Welcome to our quantum deep dive. Today, we're going to talk about one of the universe's most elusive particles, the electron antineutrino. And we're basing this whole deep dive on a really fascinating essay by Georg Owe Schnappat. So, picture this. It's the 1930s, and physics is in a total crisis. I mean, a real head-scratcher. Observations of radioactive decay seem to be breaking one of the most sacred rules in the book, the conservation of energy. It was a huge problem that set the stage for a truly revolutionary idea. So today, we're going to follow the story of this ghost particle. We'll start with why it was predicted in the first place, then the decades-long hunt to actually catch it. We'll get into its bizarre quantum nature, its job as a messenger from the stars, and what it might mean for our future. All right, let's get into it. Okay, so our story really kicks off with this deep, deep puzzle right in the heart of the atom. It's a process called beta decay. And on the surface, it looked pretty simple, but, well, it was hiding a universe-shaking secret. So, when physicists looked at a neutron decaying into a proton and an electron, the math it didn't add up. The numbers were off every single time. Energy and momentum had just vanished. Poof. And according to the fundamental laws of physics, that's a big no-no. It's impossible. It was literally like a tiny, invisible thief was sneaking out of the reaction and stealing some of the energy. So, to fix this massive headache, the physicist Wolfgang Pauli came up with what he himself called a desperate remedy, basically a ghost in the machine. Back in 1930, he had this idea. What if there was a new, totally invisible particle? It would have no electrical charge, almost no mass, and its whole job would be to carry away that missing energy. It was the perfect way to balance the cosmic books. And this hypothetical particle, well, it eventually got a name, the Electron Antineutrino. It's the antimatter partner to the neutrino. And if it existed, it explained everything. The laws of physics were safe again. But here's the catch. It was just an idea, a really clever fix on paper. It would take more than 20 years of pure ingenuity to prove this phantom particle was actually real. Okay, so proposing a particle is one thing, but actually finding an invisible one that can pass through matter like a ghost, that's a whole other level of difficult. I mean, seriously, how do you even begin to catch something that barely interacts with, well, anything? And it was a long journey from just an idea to actual reality. After Pauli threw the idea out there, the great Enrico Fermi formalized it. But still, the particle was a ghost for 26 years. It wasn't until 1956, in this really groundbreaking experiment, that scientists finally cornered. So physicists Clyde Cowan and Frederick Rains came up with this brilliant trap. They used a nuclear reactor which just spews out antineutrinos, and they looked for a very specific, unique signature. They were looking for a double flash of light, two distinct flashes happening just a few millionths of a second apart. If they saw that specific double flash, that would be the smoking gun. That would prove they'd finally caught their ghost. And they saw it. They actually saw it. The ghost was caught. This was a monumental achievement. It validated a huge piece of the standard model of particle physics, and almost 40 years later, it earned Frederick Rains the Nobel Prize for the discovery. Right, so they proved it's real. Awesome. But catching the particle? That was just the beginning. Figuring out what exactly they had caught, well, that opened up a whole new can of worms. And this is where the story gets really, really weird, as we dive deep into the quantum realm. So get this, it has zero charge. Its mass is so tiny that we still have only been able to put an upper limit on it, and it only interacts through the weak nuclear force. That's it. It's also what's called a fermion, one of the basic building blocks of matter. Now you put all that together and what do you get? You get a particle that could fly through light years of solid lead without even slowing down. Right now, billions of them are zipping through your body every single second and you don't feel a thing. But here's where it gets really mind-bending. The antineutrino kind of has a dual identity. It exists in two different kinds of states at the same time. Think of it like a smoothie. The flavor state, that's whether it's an electron, muon, or tau antineutrino, is what you taste. But the mass state is like the underlying recipe. It's the quantum mix of different ingredients that are blended together while it's just flying through space. And this whole dual identity thing leads to a really bizarre phenomenon called neutrino oscillation. What this means is that an electron antineutrino, Well, it can literally change its identity as it flies through space. It can start as one flavor, and by the time it gets to a detector, it might have morphed into a totally different one. It's a true quantum shapeshifter. And this is only possible because it has mass. Now, that might not sound like a big deal, but it was huge. The original standard model, our rulebook for the universe, said neutrinos had to be massless. So this discovery actually broke the model and opened up a whole new frontier in physics. Okay, so let's zoom out, way out, to the cosmic scale. Because this tiny shape-shifting particle isn't just some weird subatomic quark. No, it's a key player, a crucial messenger in the most violent, most energetic events in the entire universe. Yeah, antineutrinos are being cooked up in the fusion furnace at the core of our sun. They're born in the titanic explosions of dying stars. They're even created from radioactive decay deep inside our own planet. They really are cosmic messengers, and they carry pure, unfiltered information from the most hidden corners of the universe. When a massive star dies, when it goes supernova, it releases a number of these particles that is just, it's hard to even wrap your head around. Just look at that number on the screen. It's staggering. In fact, most of the energy from that explosion isn't light. It's a titanic blast of neutrinos and antineutrinos. And get this, back in 1987, detectors here on Earth saw a burst of antineutrinos from a supernova hours before our telescopes even saw the light from the explosion. That one event was the birth of a whole new field, neutrino astronomy. Right. So the most important thing to get here is that their ghostly ability to just pass through anything makes them the perfect messengers. They fly straight out of the fiery heart of a star, right through dust clouds, through entire galaxies, without being changed one bit. It gives us a direct, unfiltered window into the engines of the universe's most incredible explosions. Which brings us to the future. So what can we actually do with a particle we can barely even detect? Well, as our technology gets better and better, the possibilities are becoming absolutely astounding. Well, for one, by detecting what are called geoneutrinos, the ones made by radioactive decay inside the Earth, we could basically create a CT scan of our own planet. Imagine that. We could map out where elements like uranium are, figure out what's really driving plate tectonics, and even use it to monitor nuclear reactors from a distance to make sure nobody's up to no good. And their ability to go through anything, it opens the door to stuff that sounds like pure science fiction. Scientists have already sent a coded message with a neutrino beam straight through solid rock. Just think about that for a second. Communicating through a mountain or an entire planet. We're talking about a completely secure, totally unstoppable channel for information. But maybe the biggest, most fundamental question is still out there, and there are really two main possibilities. Is the antineutrino what we call a Dirac particle, meaning it's a completely separate, distinct thing from its matter twin, the neutrino, or is it a Majorana particle, which would mean it is its own antiparticle? If that's true, it would completely blur the line between matter and antimatter. And look, the answer to that question has consequences that are just profound. If it turns out the neutrino is its own antiparticle, it could be the key to solving one of the greatest mysteries in all of science. Why is our universe made of matter? Why didn't matter and antimatter just wipe each other out at the beginning? Answering this could literally tell us why we and everything we see exist at all. So this ghostly particle, which was born from a crisis in physics and detailed so well in Jörg O. Schneppat's work, has really become a key to understanding our universe on both the tiniest and the grandest scales. It really has. And to learn more, we absolutely recommend you visit schneppat.de. Thank you for joining us, and goodbye.
Schneppat.de is a private project by Jörg O. Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.